When we originally derived the Rayleigh distribution, we said 4 assumptions about distributions of X and Y. We now want to look at when we take away 2 of those assumptions, namely that they are identically distributed and having the same variance, and that they are statistically independent. What happens if those 2 assumptions don't hold? We're going to measure things by how close are they, how close are approximations in coming up with the approximations of the CEP, circular error probable. And remember, what did circular error probable mean? The CEP is a circle where the probability that your misdistance is inside that circle is 50%. It is the median misdistance. So that's what it means, and that's how we're going to compare approximations. Because without those 2 assumptions, we no longer have this nice radially symmetric PDF, joint PDF. We have cases of these ellipses. So the method to evaluate is to numerically calculate the CEPs with these other ellipses and see how close approximations get to that same CEP. Here's about 4 different ways to do the approximation. Let me concentrate on the Rayleigh here. Remember, if I had a true Rayleigh with all 4 assumptions holding, I got a CEP with this formula, at least approximately, where this sigma was the sigma of both the X and Y distributions. Now, instead of, because the X and Y are different, we're just going to use the average of those 2 guys. So you can either write it this way, where it's the same number here in front times the average sigma, or write it this way. This 0.5887 is just half of this number. The rest of these are other approximations. This is a linear approximation where the sigma mean and sigma max mean between the sigma X and Y, which one's smaller, etc. I won't go through comparing all 4, but as that ratio between the 2 gets closer to 1, the more the sigma X and sigma Y are close to each other, the better any of them get to truth. The green one is the truth. It's kind of hard to see in it. But they all get close to truth as you get close to 1. And it's only kind of down here where the ratio between the smallest and biggest is under 0.2 that you can start getting into trouble. This looks bad, but this peak here is only 2.2%. So if you look at that Rayleigh guy and you're happy with being within 2.2% of the true CEP, here's up there and down here about ratio of 0.15. You're still within that 2.2%. What does that 2.2% mean? What does that 0.15 mean? Inverted, that means the larger sigma is 6.7 times the smaller sigma or less. If you look at any of these ellipses shown, even this most elongated one, I don't think the sigma along the long axis is even, I don't know, 2 or 3 times along this other axis. We have to have a really elongated ellipse before you start getting bad approximations using the Rayleigh approximation. So all that is a way to say those 2 assumptions aren't that confining. You can get rid of them, and the Rayleigh distribution still does a pretty good job, at least as measured by how close it calculates to CEP. It's kind of long, but it's worth knowing. Next, we'll show what happens. What if you're not given a sigma? You've got to determine it experimentally.